In this video, we're going to compare MO theory interpretations versus hybrid and VSEPR theory interpretations. If we were to think of our dinitrogen, if we tried to bond, this would look like I might still have triple bonds, or maybe instead of knocking an electron free, I just break a bond and one of these electrons leaves. There's a couple ways to think about how to draw a nitrogen cation. When we think about this for dioxygen, well, if I have a dioxygen cation, I either have a radical or one of my bonds breaks, and I still have a radical, and just one of them short an electron. So there's a couple ways to think about how to draw these, but in general, we've destabilized the molecule. Making a cation tends to knock electrons either out of bonds or out of orbitals and destabilize it. There's two ways to interpret this. Either our bonds should be weaker, or there's less negatives around and our atoms should be able to get closer. If there's just more positives, then they want to hold on to those electrons all the more. And so we kind of have both possible theories. Either our bonds will get further apart and weaker because we're breaking bonds, or our bonds should get stronger because with less electrons, we can shrink and pull in. Well, what do we actually see? Well, if we have our standard pattern, sigma, sigma star, sigma pi, pi star, sigma star, we're going to see the same pattern all the way across. Well, nitrogen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nitrogen plus, 1, 2, 3, 4, 5, 6, 7, 8, but only 9. It lost one electron. A bonding orbital has lost an electron. If you think about the bond order, well, 2, 4, 6, 8 minus 2. 8 minus 2 divided by 2, so 3. Dinitrogen looks like it has a bond order of 3, which is kind of what the valence shows us. If we do our N2 plus, well, I've got sigma bonding, and 3 from my pi, so 2, 4, 6, 7. 7 minus 2 divided by 3 for 2.5. My bond order should be weaker. And what we find if we actually look at it, it's a nice table on 461 in the book, but dinitrogen's bond energy and bond length, 945 and 110 picometers, kilojoules per mole and picometers here, compared to the cation of 841 kilojoules and 112 picometers. What we see is that we have a weaker bond. I have less electrons holding it together, so the bond has gotten weaker. If I do this for dioxygen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, those are pi antibonding, or pi. Sigma antibonding, sigma. If I think about my bond order, 2, 4, 6, 8 bonding, and I have 2, 4 antibonding. So 4 divided by 2, bond order of 2. Oxygen plus, the cation species. Well, it's going to have 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we add up our bonding and antibonding, bonding, there's 8 bonding. But now, 2, 3. It's only 3 antibonding. 5 divided by 2, 2.5. Our bond order has increased for the O2+. And if we look at their energies, dioxygen is 498 kilojoules per mole, but the bond in O2+ is 623. The length was 121 picometers, and it goes down to 112. We knocked an electron off. Why did oxygen get more stable? Because you lose your highest energy electron. If you'd lost any other electron, one of these had left, well, your higher orbital electron would have just fallen down, would have gone to take its place. So you always lose your highest energy electron, and the result is that is a antibonding electron for dioxygen, where it was a bonding electron for dinitrogen. Breaking one electron off of dioxygen actually creates a stronger bond. Now, the molecule itself is less stable. It definitely wants more electrons. Oxygens are very electronegative. But in terms of just the bond strength, you now have more electrons proportionately pulling together versus pulling apart in the cation than you did in the neutral atom. And so our bond order increased from 2 to 2.5. So molecular orbital theory lets us see what we see in the real world played out in our actual depictions. Lewis structures, hybrid orbital theory, again, can't really show us this or doesn't make it clear which possibility is being followed. The fact that one of our dimers gets weaker and one of them gets stronger as we add a cation wasn't possible to be determined from our Lewis structure. And so MO theory again helps us explain some of the properties we see in more detail.